Welcome back to how to train your AI to play Breakout. In the last episode, we looked at how we can modify the observation layer, trimming, grayscaling, monoscaling, as well as adding an aimbot that helps our AI to predict where the ball will land. And then we did some manual hyperparameter tuning. For example, changing the frame stack and see how the model performs with different number of stacked frames that give it kind of a memory of where the ball was before. Now that was a highly manual process. We had to choose a parameter set, we had to rerun the model and then look at the results and decide which parameters to test next. And basically what I ended up doing was vary each parameter independently. Now luckily there are better solutions to do that, and I've chosen to use the Optuna Framework, which allows me to specify a search space, which allows me to tell it, okay, look for every frame stack between 1 and 20, look for every number of environments between 1 and 50, and so on. And within that defined search space, it will try to find the best set of hyperparameters. Luckily, the Optuna framework integrates really nicely with OpenAI's GIM and the stable baselines model, so it was quite straightforward to bring it together and get it to run. Let me try to summarize my understanding of the Optuna framework. We have a so-called objective function, which is a function in which we do all the programming around creating a model, creating an environment, and telling the model to start training. And in the end, the objective function hands back a score, and what it takes in is a trial. And this trial defines the attributes which we use for training. So for example, the number of environments for our vectorized environment, or our learning rate, which might be something like 2 per mil. The score goes into the so-called sampler, which is the entity which tells us this is going to be the next trial. So the sampler decides on what hyperparameter combination to try next. Now when we map that to our understanding from TensorBoard, where we have something like the score on the y-axis and the number of time steps or the time to train the model, and there for a single trial we will have a line that might look like this, and at some point at the end we evaluate the score, and that's the score that's handed from the objective to the sampler. And then we're going for another trial, and that one might perform a bit worse, and then the sampler decides to try something different, and that might perform a bit better. Now let me clear up a bit. Now each of these lines on TensorBoard will be one circle here. So first we did the red one, and then the sampler came up with a new set of parameters and did the green one, which performed worse, and lastly he came up with the blue set of hyperparameters. There's an additional concept in Optuna enabled by default, the pruning. And you can imagine that as, let's try a new set of parameters, let's add one more line here, and if that line performs poorly at the beginning, then at some point the objective function will just cancel it and say, okay, let's not waste more time on this this bad trial, and let's try the next one. So you can imagine this as going for another circle, and within the objective function saying, no, this one doesn't work, let's try the next one. Now let's look at the code. I'm working on the 4.0 wrapper Optuna_PPO, which is a set of code that just does a bit of hyperparameter tuning on some of the parameters, but only goes for a PPO model. And the first main difference that you see is that we are using a custom callback for the evaluation, which inherits from the eval callback. And the main difference to the eval callback is that we report the last mean reward and the number of the evaluation to the trial object, and that we check whether the trial should be pruned. And if it should be pruned, we make sure that the onStep function return false, which basically tells the training to abort. Now the next big piece in the code is the objective function. The objective function itself just takes the trial object as an input, and I have created a creation function around it to be able to set some of the hyperparameters, the parameters that just stay the same across all of the hyperparameter tuning. So things like how many evaluation episodes do we want, how often do we want to evaluate, and how many environments do we want to vectorize for evaluation. Now in the objective function, we'll first find the model parameters and then the environment parameters. And this trial.suggest basically tells the sampler that this is what you can change, this is what you can vary, and where you should try different combinations. And you see that I have actually not done any tuning on the model parameters because they're all hard-coded. I've only tuned the environment parameters. When I looked at some other people's codes and how much score they would achieve in Breakout, I actually found that I did not consider which environment to run in, whether to run in the Breakout v4 or v4 no frameskip or v5 environment. And I recommend that you have a look at the documentation of them, and when you go to the main page you will find a general description of what they implemented it and why they implemented it. The summary is that in version 4 we have no stickiness of actions, so the buttons will not stick, they will not kind of repeat the last action sometimes instead of taking what the model predicts. But version 4 would have stochastic frame skipping, so sometimes just a frame would be missing. And version 5 would be having stickiness but no stochastic frame skipping. I have not tried the version 0, but I used also a variant of version 4 with no frame skipping. After defining the parameters, we proceed as usual. We create the wrapper classes, we create the environments. What is noteworthy is that the number of environments for the training is defined in this dictionary, whereas the number of environments for the evaluation is a hyperparameter. So we make sure that during the whole hyperparameter training we still use the same number of evaluation environments. This line is particularly important because it tells the evaluation callback when to stop the training and when to make an evaluation. And later, when we look a bit deeper into the Optuna, we will find that Optuna will not make sure it happened at the exact same training step or at the exact same training time. That's up to us when we implement this. And with this normalization that we say we have, let's say 1 million training steps, we want to evaluate exactly 4 times, and we then divide by the number of training environments. And this last one may actually vary, and we need to account for that such that the first evaluation always happens at the same number of training steps in order to allow for a fair pruning. When we train our model, we will from time to time stop the training and evaluate the model, and this is defined by the eval frequency or the eval steps. And let's say this happens 3 times in this model, once here, once here, once here. And now we train a second model with slightly different hyperparameters, which looks like that. But now the evaluation steps are not at the same point in time, like we would expect, but we made a programming error, and for example it would evaluate here, here, and here. What Optuna does, it compares the first evaluation with the first one, the second one with the second one, and the third one with the third one. So what would happen is that even now we as humans see the red line is definitely outperforming the green one. Optuna would maybe prune it because it performs in its eyes worse on the first evaluation. The first evaluation of the green model being here and the second one being lower. And there are some cases where it's not obvious which model is performing better. It always depends on what you choose as the x-axis. Do you choose the number of training steps Or do you choose, for example, the time? If we train a model with less frame stacking or with less vectorized environments, we often end up in a higher number of iterations per second. So at the same step, the model might perform worse, but at the same time in the training, it might perform better. So this line of code is really important in the sense that we need to define the evaluation callback to be called at points that we want to compare, be it the same time, be it the same number of training steps, or something else. To illustrate this, let's look at TensorBoard. I have chosen two trials that have very different frames per second, so one that is really fast, one that is really slow. And you see, if we take as the horizontal axis the step, then at the second point of evaluation, the green one is worse than the red one. But if we look at the relative horizontal axis, meaning the time spent for training, we actually see the green one being better at a specific time. Still, the evaluation points in my example are chosen such that they are at the same step, not at the same time. So Optuna will here tell us that the green model is worse than the red one. I have actually spent several hours debugging my code until I found that I had an error in this exact line where I used the number of evaluation environments here instead of the number of training environments, and that kind of made Optuna prune the best trials and keep the worst ones. Now going on in the code, we see that we define our model, we tell it to train, we save the model, and in the model saving I'm using the trial.number as the identifier, as the name of the file. In order to kick off the hyperparameter tuning, we instantiate the objective. I've selected 100 eval episodes, far more than we had before, because since now we do pruning, we want to minimize the uncertainty in the evaluation step. We want to make sure that if we prune a trial, it better be a bad one. And the evaluation frequency is much lower as before. Now here the evaluation frequency, as you've seen before, is something like how often should it prune in a full training run. And in our previous videos, we basically evaluated the whole time, every 5,000 steps or so. Now we only do it 4 times because it is really expensive since we have set the number of evaluation environments so high. Then we tell Optuna to create a study, and the study should maximize the objective function. And what I found really neat is just specifying an SQLite file. If it doesn't exist, it will create it. If it exists, it will just load the study, meaning I don't have to start from scratch the whole time. The whole hyperparameter tuning that you see here has been the work of several days, and if I would need to have started over all of the time when my code failed, it would have been weeks easily. So I recommend to do that, and we will look into that database in a few minutes. And now let's look at what this code has actually produced over the last few days and, well, a lot of my electricity bill. And you will see that there are many trial runs that stop after 250k training steps. You will see a lot more stopping after 500k. And after 750, there are almost none left. So you see the pruning really happens in the first 2 evaluation steps. And this is where the model decides this trial is not worth running. You also see one very bad trial at the bottom that continuously ran. That's because this was one of the first ones, and the pruning depends on the order in which the trials are run. So if the first run is really bad, it will still proceed to the end because it has no point of reference. But if a run happens at a later point in time, it will need to compare itself against a lot of contestants. So the later in the tuning process a trial happens, the less survival probability it has. One recommendation to really speed up the tuning process is to define the first few trials manually and select some of the best known hyperparameter sets that you either know or imagine. This is because once you have established something like 5 trials already that are good, then all the subsequent trials need to measure up against those and can be pruned early in the process. And you can achieve that in the code with these grayed out lines. Just study.encube trial and then define the hyperparameters. The reason why I grayed them out and I commented them out is that I've rerun that code over and over when the tuning process would either be cancelled by me or run into an error. And each time you execute these lines, they will be added as new trials, so the system will rerun them. And I ended up in a situation where I ran these 6 different trials over and over again. So make sure you add them, but you only add them once. So you need to be mindful that the state of the database which defines your study does not automatically sync to your code. And when I re-execute the line that adds another trial, it will just add this line to this table. At the end, we'll call it waiting, and we'll wait until it can be run. Now this database is worth another look. In the main table you will find the attributes like trial ID and number. Be a bit cautious, it's not the same one. I fell for that in the beginning. That's why I deleted some trials that I should not have deleted and kept some that I should not have kept, because the number is what I use to define my file names and my tensor board names. And then I just looked at the trial ID instead in the different tables, and that created some error. Besides this main trials table, I find noteworthy the one with the intermediate values. So these are the values that a individual trial has over the different evaluation steps. So you will always find 4 steps in here, because I have made sure that I've always used 4 evaluation points. And you see the Optuna study has no chance of actually telling at which point in time or at which training step these individual values were created. It only knows this step. So you really need to make sure that step 1 of this trial is comparable to step 1 of this trial and to step 1 of this trial. And in the trial_params you will find the different hyperparameters that were chosen for each trial. Now all of these numbers that you find in the database in the different tables you also have available in the study object in Python. So it should be straightforward to you to now use these numbers to come up with your own analysis on how much impact which hyperparameter has. But of course you can also use some pre-built functionality from Optuna. In the documentation we find several functions that allow us to explore the importance of different features, how much impact a hyperparameter has on the objective, and you have several functionalities for the visualization, of which we will now explore the contour run, which I find particularly beautiful. In the study_explore code you will find that we just load one of the pre-trained studies from the SQLite database and then plug it into different visualization functions. So let's run that code. Now in this parallel coordinate plot you see the different combinations that have been tried and what scores they have achieved. And there's a bit of a red flag, because I'm pretty sure I also asked the hyperparameter tuner to go for higher frame stacks, to try more and less environments, and definitely to try out different environment IDs, and it seems not to have done that. This becomes also evident in the contour plot, which is produced by the next line of code. Here we would expect something like 40 different black dots, because we have run 40 different trials, but we only see less than 10. The reason for this behavior is that Optuna only looks at the set of trials that have been completed, meaning they have not been pruned. So you will see a highly biased picture in the sense that only those trials which have been good enough to not have been pruned to be visualized. So all the trials that have been pruned, which kind of provide very likely worse values, are not kind of seen in this picture. And I have reached out to the Optuna community on their discussions page on GitHub and asked this question whether this understanding is correct, and the answer is yes, it is correct. Only those pruned trials, only those completed trials are considered. But they also provided me with a code that would actually convert the study in a way that takes a pruned trial and converts it into a completed trial with a predefined value, which I can set. So you can find that as the next section in the code. It's a function called setPruneToValue. You provided a study object and a value. And what it does, it takes all the pruned trials and sets them as complete, and then changes the value to the provided one. And when we run that, and then redo the two plots, we will first see a much more crowded picture on the parallel coordinate plot. We will see all of the 3 different environments being tested. We will see much higher frame stack numbers and objective values. And most importantly, we will see a lot of the trials going to 0, with 0 being the placeholder value I've used for proof. And on the contour plot, you will also now see a much more complete picture with a lot of trials just going to 0, which is white on the contour plot. On the environments, we see that the breakout no frame skip environment performs best. This is intuitively reasonable because the V4 has the stochastic frame skip, just randomly remove frames, which makes life harder for our AI. And the V5 has reintroduced the sticky buttons, meaning that even though the AI tells it to go left, sometimes it will just go right. And that also makes life harder for the AI. We also see that the sweet spot for the number of environments is not necessarily a high number of environments. Intuitively, I would have expected the more the merrier, more environments, meaning, well, more precise training. It would, of course, come at a cost of performance, but we're not looking at performance here. We are looking at the same number of training steps, and if there are 1 million training steps on 8 environments, I would have expected it to be worse than 1 million steps on 10. But it doesn't hold true. There seem to be a few sweet spots between 5 and 10. And on the frame stack, we also see that more or not necessarily better, that there seems to be a sweet spot at 2, 3, or 4 stacked frames. On the frame skip, we see a sweet spot between 2 and 3. Now the frame skip, what it means is that the same number of training steps just play through more games, because more frames are skipped, so the whole thing is faster. On the other hand, it reduces the fine sense for moving the pedal around. Because if we skip 3 frames, then it means it will take in between always the same action. So 1 going right will translate into 3 frames going right. So it will not be able to fine-tune the pedal as much if the frame skip is too high. So now that we have run about 40 different trials for about 10 hours, we can select our best set of hyperparameters and make another study. I just called that study 2, and I told it to train for 10 million steps, but I actually only let it run for 1 trial. Now a few trials in study 2 have been calculated. Let me show you the results. The blue curve is our reference from the chapter 3.3. And now let's start the trials from study 2. So the first one, first it looks promising, but then actually doesn't make that much of a difference. The second one is even worse than the original one. And the third one doesn't even appear. So it actually has exactly the same pattern as trial number 1. And the same goes for trial number 3, which also has the exact same pattern. So trial 1, 2, and 3 have the exact trajectory. In the database for study 2, let's open the trial parameters. And we are comparing the parameter values for the trial IDs 2, 3, and 4. And we see it's 1335, 1335, 1335. So what happened is we just reran different trials but with exactly the same parameters. So let's try to figure out what happened in the code. I have loaded the study 1 object from the database with the row 166 and then ran it through this function to get the study trials as a nice data frame. And now let's open the data frame and look at it. It's already sorted by the highest values. These two have been the ones that have been executed in study 2, and the first one has been executed once. It's with 6 environments, and this one has been executed 3 times. So it's not that I re-added the same trial several times in study 2, but study 1 already gave us a repetition in these. What is a bit confusing to me is this is not a trial that came from my manual adding. I've mentioned it before. During this manual adding, I've rerun it a bunch of times, which caused some confusion. So somehow the sampler came up with the same trial several times. It might be because of the way I've used Optuna, that I stopped it, started again, stopped it, started it again, or some other error that I have made. Now, finally, the rest of the trials have finished. Trial 1, 2, and 3 are the same one. They run with the same parameters, so, well, they all have exactly the same curves, which is kind of boring. But at least we have trial 4 and trial 0 as well, so we definitely have 3 different trials that went for the full 10 million training steps. So let's compare it to the baseline that we have. And you see we have a slight outperformance by one of the trials. The other ones are more or less the same. You see there are 2 trials that slightly outperform our baseline, trial number 0 and trial number 4. And trial number 1 is slightly worse when we look at the training scores. When we look at the evaluation scores, it looks a bit nicer. Remember that the evaluation frequency is very different between the studies and the baseline. In the baseline, we have measured the evaluation every, I think, 5,000 steps, whereas here in the Optuna studies, we are only measuring 4 times for the full training period. And we see that trial 4 far outperforms the other ones, which is great news. Let's see how it plays. It's making a little hole on the left side and getting the ball up there, stuck between the bricks and the ceiling, which is a really neat trick that it seems to have learned. And it gets up into the 400s really easily. Okay, now it seems to struggle a bit. But overall, very impressive work. So now let's look how 9 environments are doing at the same time. We see they are doing things almost perfectly in parallel. There's a little disjoint to the right lower one and the right one in the middle. Okay, but all of them go up beyond 400. Now, when we look back to what we saw in chapter 3, when we let 9 environments play the same game, it was not so perfectly synchronized as we see here. And the reason for that is that now we have chosen breakout no frame skip, meaning we have no stochastic frame skipping. There's no randomness in the environment anymore, because no frame skipping and v4 doesn't have any sticky buttons. The only stochastic element that we still have in there is the model itself, because we run it with deterministic equals false, meaning sometimes given the same observation space it might perform a different action, and the actions are weighted with their respective scores. Now we look at how the new model performs on Breakout version 5 on the left versus the old model from chapter 3 on the same environment. And we immediately see our new model is very bad. It can get barely up to a score of 10, even though before it went up to scores of 400 and did some really impressive work with, making the hole on the left and getting the ball up there, which was really cool. What's happening here is what I would call the equivalent of overfitting. It basically memorizes the exact sequence of actions it needs to take without any kind of what we would call understanding of the environment. When we have some stochastic elements in our training environment, some randomness, we force the model not to only memorize the sequence of what it does, but to actually react to slightly different states of the environment in an appropriate way. So now we are at a bit of a philosophical crossroads. We have a model that performs really well on the original game, on the game as it would run on the Atari 2600. But we know that if we just change a little bit in the environment, it will perform badly. You can read more about this problem in the Atari Gym library documentation. There's a chapter on the stochasticity and why they have implemented and how they have implemented the different stochastical elements. Or you can just say, I have a model that performs really great, gets into the 400s goals, job done. If you want to dive a bit deeper and if you want to train your model to not only memorize the exact sequence of buttons it needs to push, but actually be able to react appropriately to slight changes in the environment, let's take a step back to the evaluation callbacks. On the left side, you see the training of the model, where we just go through many training steps, where we feed an action into the environment. It provides a new observation, and based on that observation, the model predicts the next best action. And every now and then, we would call the evaluation callback on the right side, and it would run its own version of the environment and maybe even its own version of the model, depending on how you exactly configure it. And here we can now hook up a bit of the thoughts around the randomness. So we have seen that if we train our model on a non-stochastic environment, it will just learn the exact sequence of actions. We need to add enough randomness to the training process in order for the model to be, generic enough. So on the training, we definitely need it. On the evaluation, it's a bit the question what we want to achieve. Do we want to have the model play a perfect game, get an as high score as possible? Then I would say we use the non-stochastic version, because the stickiness of the buttons makes life a bit harder for the AI. The frame skip makes life a bit harder for the AI. And the non-deterministic actions as well. On the evaluation environment, I find the answer less clear than on the training environment. You might argue that you want to have the deterministic environment to really have a comparable score against other models, and because it's the original game. On the other hand, if you run the deterministic evaluation environment, you might not spot overfitting or memorizing of the sequences. So that's a bit up to you. It's a choice you need to make. The summary here would be the choice of environment really matters, and understanding your goal and priorities really matter. Now, the three elements that we have come across now to add some randomness to our environment and to the model. On the model side, we have the deterministic flag. And this deterministic flag basically says, should the model always take the action with the highest score, or should it most probably take the action with the highest score? So basically it's still a random variable. On the environment, we now have seen two things. We have seen the stochastic frame skip. So once in a while, just skip a frame. And we have seen the sticky buttons. And of course, it's not that simple. There's more. I made a section on my GitHub called Devil in the Details, trying to explain this. Let me give you a summary of it. I looked at the blog post from Vincent Müller, and he was able to make an impressive model and an impressive gameplay out of an extremely short section of code. It's the A to C model. It's trained on breakout, no frame skip, and the prediction is purely deterministic. So, considering what we have discussed so far, this should mean that this is a completely deterministic environment and a completely deterministic model. But when we look at this nice video of his, it doesn't look deterministic. They are not in sync. They're playing kind of, slightly different games. So I reproduced his code. I ran it for also 10 million steps, and I got the same picture. He actually, out of a purely deterministic model and purely deterministic environment, he gets a non-deterministic behavior. The reason for this is in the Atari wrapper that he is using, which is using the no-op reset environment, which is a wrapper around the deterministic environment, adding a bit of stochasticity. It basically adds between, I think, 0 and 30 no-op operations, meaning the first up to 30 steps, the model is not allowed to interact and just has to watch. So it seems he found a way to efficiently train a robust model on a deterministic environment using this Atari wrapper. I ran the same model trained on the same environment on the breakout version 5, so the one with the sticky buttons. And there again, the model performs as poorly as the one we created. My suspicion is that instead of memorizing one exact sequence, the model just memorized 30. There were only 30 different starting options, and for 30 different ways the game could go if it's fully deterministic. So my guess would be if we just increase the number of environments, we would just see the same 30 games over and over again. But this is more of my personal hunch. I didn't do a deep investigation. For those who want to dive a bit deeper into the stochasticity, I recommend to read the blog post from Nicolas Marquier. I found it a very good summary pointing to even more in-depth readings, and it helped me understand the different ways, and also it had a look at the different pros and cons of the methods. Thanks for sticking with me this long. Even though we didn't get to a new great model that outperforms our old one, I still feel it was worth the time and effort. I learned a lot about the different choices to make in reinforcement learning, and I hope you enjoyed it. Thank you very much and have a nice day.